do, or at least a lot of organic classes will go through and do, is throw a ton of relatively simple Lewis structures at you. The whole point of making you do hundreds of Lewis structure problems is really to only get you in the habit of recognizing particular bonding patterns. I already mentioned one for carbon. Carbon has how many bonds? 4. Right? It says nothing about single, double, or triple. It just says I need 4 bonds around carbon. If I look to nitrogen, one of the things that you'll learn as you start to draw lots and lots of Lewis structures is that nitrogen is happy with 3 bonds. Okay? The whole reason we make you go through all those Lewis structures is not for the sake of drawing Lewis structures, because ultimately these rules that we're talking about kind of get set aside and tossed out the window when we move to larger structures, because the larger structures become even more of a pain to try and come up with based on these rules. But you have to have an understanding of how those different atoms can connect, so that when you look at a structure, you can say, ah, that's a bad structure. Right? And you know the reason why. Right? So let's pick. Did we do carbonate? I'm hearing some no's, so let's stick with carbonate. So if we stick with carbonate, to start this off, we'll look at the total valence electrons. Carbon brings in how many? 4. Oxygen brings in 6 times 3, which equals 18. And we got the negative 2, whoops, our charge, which is negative 2, which means we add in 2. So we have a total of 24 electrons that need to go into our structure. Right? This gives us an idea of what has to be represented in this. So it can help us out even with larger structures. We can now decide what our central atom is. Carbon is the least electronegative. It can bridge, so it'll be my center, and I'll scatter my oxygens. I can then add my valence electrons in pairs, and I will put them around the oxygens first. Why the oxygens? Oxygen is more electronegative than carbon. Why is that important? Electronegativity is a measure of holding bonding electrons. The oxygen should take the electrons away from carbon. Once I've got my basic structure, I will now start, I added my total electrons, and I'll now convert my pairs into a line. I noticed one student converted all pairs into lines. Okay, there's nothing necessarily wrong with that, but again, I'm just trying to delineate a difference between a bonding pair and a non-bonding pair. So the only thing that I'll convert into lines will be bonding pairs. So any place I have a pair of electrons between atoms. Okay? The next thing is to satisfy the octet rule by moving electrons. So if we go through and look at this, all of our oxygens have their octet satisfied. They all have 8 electrons. But what's going on with carbon? 6. Okay? It only has 6 electrons around it, so it has not satisfied its octet. So what do we have to do? We have to move a pair of electrons towards it. So I can take a pair of electrons from the oxygen on the right. And I now have an octet around the carbon. I've not lost the octet on the oxygen because I can count that bond for both atoms because it's shared between them. Okay. Last thing I would need to do is go through and calculate formal charge. Okay. We can already guess that our formal charge on this molecule should total to be. How do you know it needs to be negative 2? That's what the formula says. Okay. Our formula is CO3 minus 2. It has to have a negative 2 charge. So when you crank that out, you should find that your oxygens with the 3 lone pairs are negative. The carbon will be neutral, and your oxygen with 2 lone pairs will be neutral. Okay? This gets into the bonding patterns that we would expect to see. Carbon with 4 bonds, I don't care where those 4 bonds are, but as long as it's got 4 bonds and nothing else, is happy, neutral. An oxygen with 2 bonds and 2 lone pairs is neutral. An oxygen with 3 lone pairs and 1 bond is negative. If I've drawn enough of these structures, I start to memorize these patterns. And I don't have to go through and calculate the formal charge each and every single time. Okay? That's partly why you go through and do these Lewis structures, is to pick up the patterns on when an atom should be neutral. What does it have around it? When an atom is negative, what's around it? Okay? Because again, as we move further in, we start to drop in all sorts of implied things. Okay? If we go back to our 6, to satisfying the octet by moving pairs into bonds, our oxygen on the right shared its electrons with the carbon. Did I have to pick that oxygen?
No.
No. Any source of electrons, in particular lone pairs, okay, can be moved in. So I could have just as easily picked the top oxygen or the left oxygen, which means there are multiple ways or multiple pairs of electrons that could potentially satisfy our octet for carbon, which means if I'm asked to draw the Lewis structure for this compound, I cannot provide just that one answer. I'm going to have to go through and draw all 3 possibilities. Why do I say only 3 and not for each and every single one of those lone pairs? Everybody understand what I mean by that question? So yeses and nos. Okay. What color I want? Let's pick orange. So what I'm saying is we've got those 3 structures. Why do I not have another structure where I use, say, this lone pair to make the double bond? Okay. The lone pair from an oxygen, from any pairs of oxygens or the ones that I use there, doesn't matter. It generates the same structure. So the lone pairs are interchangeable. The bonds, however, are not. Okay, so as long as the lone pair comes from the same atom, you're generating the same resonance structure.
So the original structure that you drew wouldn't be considered a resonance because it's just carbons?
True. It's not a good resonance structure, so let me draw that one up here in blue. We'll look at a couple variations here. The original one I drew was this guy. One of our abbreviations that you'll see as we move later on, and I can't wait to get there, is we stop drawing lone pairs. If I had left it the way it was, that would have been my official structure with the appropriate formal charges. That structure is bad for multiple reasons, and we'll get into the bad in a second. Bad because lots of charge. Bad because no octet on carbon. Okay, so that structure is inherently bad because I can make a better one. Okay, there's multiple things saying that that one is a bad structure. Okay? The other 3 work as better structures. Okay? We can get to another concept. With 3 of these structures, it's a bit obnoxious to have to draw all 3 of them out. So if we want to refer to a structure and kind of look at how the electrons are dispersed through the structure, okay, you can run into something known as the resonance hybrid. I typically do not talk about resonance hybrids because I find them useless to work with. If I take a look at any one of those 3 structures, what do I recognize as the reactivity? Where's the most reactive site? In fact, any one of those 4 structures, what's the most reactive sites? Oxygens, because they're negative. Carbon, neutral or positive, okay, depending on what structure I look at. So I've got an understanding of how that molecule can react. Can I erase all this? The resonance hybrid structure where's the negative charge? Okay. What I did was took an average of all of my structures and I combined them into my hybrid. So what I'm trying to show by these dotted lines, okay, is the electrons are being dispersed across those atoms. Okay. But if I'm going to do an actual reaction, I'm going to react this compound with a single atom. That single atom is going to react with what on this structure? One of the oxygens. Well, which one? The one that's most negative. Well, which one's the most negative? I don't know, there's no formal negative on any of them, so it's very difficult to interpret your resonance hybrids. You'll see them pop up to show that there's resonance there, but they're pretty useless as far as our overall chemistry and what we want to do with our structures. Okay? So we just drew this one up, and I'm pretty sure we ended on Monday with this one. Okay, so we looked at how we can move our electrons. We can go from bond to atom, and we can go from atom to bond. Okay? And we're only going within the vicinity, nearby. Okay? We can't jump through atoms. So some other rules of resonance. Okay? Our structure is pinned. We cannot rotate it, spin it, or move it. Okay? And yes, as we move through organic chemistry, we will spin, rotate, and move structures, unfortunately. But when we look at resonance, it's always pinned. We need to find a source of electrons. Okay? When we looked at drawing our basic Lewis structures, the source of electrons was relatively obvious. It was a lone pair of electrons. Okay? 2 dots. Those look like electrons. That makes sense. Okay? The next source is looking at multiple bonds. Okay? And again, I don't like calling them multiple bonds. They're really pi bonds. But I will try to maintain multiple bonds. So double bonds or triple bonds can do resonance. Okay? We also have the option of moving a single electron if we so choose. We'll talk about that a lot at the end of the semester. Okay? The one source of electrons that we can never, ever, ever move is single bonds. That is because when we deal with resonance, I cannot exchange the location of atoms. So if I look at this structure down here, I can never show an arrow, starting in that bond, moving anywhere, be it to a bond or to an atom. Right? Because what type of bond is that? Single bond. Single bonds cannot move. This is why I'm saying multi-bonds. Okay, so a double bond, we have the potential for moving. Our electrons can move within the immediate vicinity. So once we find our source of electrons, let's take a look at the structure. Where's our source of electrons? We've got any one of those 3 double bonds. Okay, do you see a difference between any one of those 3? No. So what does that mean about which double bond we should move? Upper right, lower right, left. Way to not take the bait. There's no difference. It does not matter which one we pick. Okay, so I'm going to pick the upper right one. I was waiting for you to tell me one of them, then I'd say you're wrong and do the other one. Okay? Doesn't matter which one we pick because at this point they're all the same. Okay, so now what we'll do is move those electrons. Okay? Doesn't matter which direction we move the electrons. Should we move them to the left or to the right? Is there a difference between either of those atoms? No. So let's pick a direction. Right-handed, so let's go clockwise. Now what we'll go through and do is see what that single arrow motion did. So now we've got to go through, and this is why everybody loves the beginning of OChem. So we've got all these structures that we've got to go through and draw with all the stupid hydrogens. We didn't touch anything else. So what do we do with everything else? We draw exactly the same. Okay? I took the electrons in that bond and I put them where? On this carbon. So that carbon now has a pair of electrons. All I've done now is shown the motion of those electrons. A line represents 2 electrons that are now on that carbon. Before I finish saying my Lewis structure is done, what do I have to evaluate? Formal charge. When we go through and calculate the formal charge, you will find that, that carbon is negative. Okay, that one's usually the easy one to find. Okay, anybody see a problem with calling that carbon negative?
It needs to be neutral.
Our structure needs to be neutral, which means where else in the structure, or what else needs to happen in the structure? We need to have a positive charge on this carbon. This comes back to how we draw and imply things. That carbon, we did not imply any hydrogens on. All we did was took electrons in that bond and moved them away from it. Well, if a carbon starts neutral and loses electrons, it becomes positive because electrons are negative. Okay? So if we just follow kind of the rough gist of where the electrons moved towards and away, we can pick up some of those charges. The other option is going through and formally calculating our formal charge. Where that becomes dicey is if we've implied hydrogens or not. So you have to be careful with where you're at in specifying your hydrogens. In this case, we have not specified or not implied hydrogens, so if we count, carbon has 4 valence electrons minus the number of bonds shown. 3 minus how many lone pairs? Or sorry, non-bonding electrons on that carbon? 0, which means we have +1. There's our formal charge. It does come out of that relatively nicely. Okay? Yes?
How do you know when to go from like a bond to an atom or a bond to a bond?
That's what we're just about to draw. Now that we've got this structure, what can I do? I can go back and say, can I draw more resonance? Now when we look at this structure, what do you see as the most reactive thing? In particular, when we're looking at resonance, we're looking for electrons. Which electrons are our most reactive? The non-bonding pair is now probably much more reactive than our bonding multi-bond. Why? The non-bonding pair is charged. So there's our reactive pair of electrons. We have a couple options with this. We can either move those electrons back towards the positive, which actually makes the most sense, because we want to neutralize things, which means the arrow that we can draw in between here is both a forwards and a backwards. You notice it's not an equilibrium arrow, because remember, resonance is a hybrid. Both of these structures exist at all times. So it's not, oh, I'm going this way and then this way back. It's, I'm somewhere in between all of these. Okay, so it's a new arrow. It's a resonance arrow. That's if we draw our electrons back towards the positive. So let's not be so boring. Let's see if we can pioneer and jump the other direction. We'll go from the atom to the bond. What's the result in this case? What we're going to do is draw out our structure again. For those of you drawing this out, I hope you're not drawing it in pen. Okay. All we can draw is what we have shown with our arrows. We did not move anything else. Okay, so, and then we've got our positive charge here still, right? Everybody agree with that? As it's drawn. Okay. You can disagree with the structure because the structure is wrong, but okay, understand how we got to this structure. Okay. We look at Rule 3. We have to verify that our octet is satisfied. Okay, really what that Rule 3 is talking about is make sure you didn't ruin your octet. Okay. So what do we mean by ruin the octet? What happened to that carbon? It has 5 bonds, which means 10 electrons. It's exceeded its octet. That is an invalid structure. There are 2 ways to solve this. Okay? With technology, I can go through and say, okay, I'm now going to reevaluate my previous drawing. Okay? And see if I can change my previous drawing before I flip out and erase all my work. Okay, so I look at my previous drawing and say, if I move those electrons there, I invalidate that octet. Okay, that carbon has too many electrons. Okay, so what can I do if it has too many electrons? Move electrons. Okay, well, what electrons can I move when I deal with resonance? Multi-bonds, right? If we look at that carbon in the drawing that I've provided, how many multi-bonds are there at that carbon? There's 2. I have 2 sources of electrons I could move. Which source of electrons do I want to move?
The ones you just moved there.
If I move the electrons I just moved there, what's the net result?
Back to that middle.
Right back to where I started. Okay? So we can see that. There, you guys are all okay with that? Okay, let's get wild. Let's move the other pair of electrons. Okay. But let's think back to how we want to move electrons. We want to move electrons as shortest distance as possible. So I'm going to take the electrons in that next bond, and I'm going to move them where? To the carbon atom. Which carbon atom? Why the bottom and not the top? So why not this red direction? Why is that a bad one? Because that puts more electrons on that carbon. The whole reason we went back to this is because that carbon had too many electrons. If we put more electrons on it, that's even worse. Okay, so we want to move those electrons away from it. The result is, I still have that new double bond that I formed, but now, whoa, that was a big eraser. Now I have my lone pair here. Okay? So we've just moved the electrons around. We could continue to go through and do this whole process. Okay? Benzene, which is what this compound is an actual interesting compound. Okay, so we'll give a moment here. Can I erase all of this? You okay with that? Silence usually means yes.
Yes.
Okay, I'm going to erase it all. So what we did was we moved the electrons to the atom, then we went to the bond. Okay? Well, is there another option? We could have just gone from the bond to the bond. So instead of doing it in those two steps, let's say we went bond to bond. Okay? That's a valid move. All we did was break down, or did in one step what we did in two. But we'd then also have to add this one. We'd get to the same structure. So we can move bond to bond. If we continue to play with benzene and look at all of its resonance structures, you will notice that we can end up with, sorry, I gotta make sure where I put my double bonds. This guy. I know I erased it all already, but if we compare this resonance structure to all the other resonance structures we drew, which is better? Why is this one better? It's neutral, it's not charged. Okay? This resonance structure that we just drew for this compound explains why this compound is ridiculously stable and it's very difficult to get it to react. Okay? Because those electrons, instead of being located in just the double bond or just on two carbons, are now shared throughout the entire ring, which means you'll often see this structure drawn out. I'm going to jump all the way to abbreviate it and get rid of those stupid hydrogens, like this. Because what are we saying? All the double bonds on the inside are now being shared equally all the way around the ring in a circle. Okay? So that would be our hybrid structure. Okay? So in resonance, we're bouncing electrons around. We're trying to see how they can move and how they can stabilize their structure. Okay? Things to consider. We can't break octets, and we're trying to stabilize things as best as possible. So for instance, if I run into a structure, say like this one. Can I draw a resonance structure for this? To do resonance, what do I need? I need a multiple bond or non-bonding electrons. Do I have that? I got both those. Hey, that's cool. So let's give it a shot. Which one do we want to look at first? Non-bond or the multiple, non-bonding pair or the multiple bond? I heard non-bonding first, so we're going to stick with non-bonding first. So I'm going to start my arrow where my electrons are. Since we're saying the non-bonding pair, it's on that oxygen. Where can I move those electrons? I can only move them to the bond. There's no other place to move them. Okay, so I will move them to the bond. So I've done my single arrow pushing, and I now want to see the result of that arrow pushing. Right? So avoid formal charge for the moment, but that's what my arrow shows. Everybody agree? Is that structure a good structure? Why not? Carbon has exceeded its octet, which means my initial arrow pushing was bad. Right? So I now have to go back to that structure and decide or move another pair of electrons. Right? Well, I've got the pi bond that I just made, or the multi-bond that I just made, so I could move that right back to the oxygen, or I could try and move the other pi bond. Right? Where can I move the other pi bond? Oh, that's interesting. I heard to oxygen. What's the net result?
End up with 3 bonds on the carbon versus 4.
We take those electrons back to the oxygen. We end up with a result that is identical to what we started with. Okay? So what would we say? Is that a valid resonance? Nope. We didn't draw anything new or different. Okay? So here's a misconception that a lot of students like to try. So let's try this one. Moving them to the oxygen is boring, didn't do anything worse. So let's take those electrons and let's move them down here. Because I can move bond to bond. That's valid. What's the result? Lots of things are wrong with this. Okay. Well, I don't even care what that atom is. That's actually irrelevant to our point. What happens to the oxygen? Okay. One lone pair formed the double bond. The other double bond went away from it. Our oxygen is now positive. Has less than its octet. Should oxygen ever have less than its octet? Why not? It is the second most electronegative element on our periodic table. It is never going to be out of its octet. It always needs to have 8 electrons. So that's a horrible issue. What's our other horrible issue? Our whole point was that carbon had too many electrons to begin with. And that arrow pushing did what? Did nothing to fix the carbon. Right? Because remember, we can only move from atom to bond, or bond to atom, or bond to bond. If I move bond to bond, the absolute furthest I can get, do the electrons ever stop being associated with the carbon? No. What does that mean about resonance with the lone pairs? There is none. We moved the electrons down, said that was invalid because it exceeded the octet on the carbon. So we moved the electrons back. Well, that's right back where we started. No resonance. We moved the electrons down, but then we tried moving the other pi bond away. Still was an invalid structure. So what does that mean about resonance with the lone pairs? There is none. Right? Interesting process. What did we just do with all of that work? It's going to sound worse than nothing. We failed. We failed at moving the electrons. That's valid. We've now learned that the lone pairs not going to be very likely to be jumping off that oxygen. Okay? That's fine. That's a good thing. Okay, so our lone pairs can't move. So, did we have another source? What were our sources of electrons? Lone pairs and our multiple bond. So we can go to our multiple bond and we can move those electrons. I should have done this with multiple colors here. So we're going to go left and we're going to go right. Okay? The right one, which we'll come up with why that's so funny in a second, I'm going to move the electrons up to the oxygen. For the left one, I'm going to move them down to the carbon. Our oxygen will pick up a negative charge. Our carbon will pick up positive charge. We look at our left one, what happens? Oops, I should be showing that carbon. All right. All we've done is take the multiple bond and take those 2 electrons and put them on the atoms nearby. Between those 2 structures, either of them good?
The right one.
Okay, both of them are bad. Okay, why are they both bad? Charge, acceptable. Another reason why they're bad. Octet. And the structure on the right, our carbon is missing its octet, and the structure on the left, our oxygen is missing the octet. Did I do that right and left? Yeah, I did. Okay. Okay. Both of them are bad. Is one better than the other? Why is the one on the right better than the one on the left?
Because the oxygen has charge.
Yes, the oxygen has its octet. I don't quite accept that answer. Why do I care about a negative charge on oxygen? It's more electronegative. If I'm now looking at where the electrons are most likely to spend their time, they're going to spend their time with the oxygen. The structure on the left makes no sense because carbon is now being shown to take electrons from oxygen. So that answer is completely nonsensical. How do you spell nonsense? Is that close enough? Okay. The one on the right may not have an octet, but at least I'm pushing the electrons where they should. Why is the structure on the right actually a pretty phenomenal structure to have? If I ask you how this compound reacts, and we look at just the Lewis structure, okay, the Lewis structure I'm about to box in black here. There's our Lewis structure. I say, how does this compound react? Well, to figure out how it reacts, what do we need to look for? Electrons, but a little more general than that. Those of you near the wall should be panicking, right? Maybe even in the floor. Looking for charge. Charge is what determines our reactions. So if I look at that molecule in the black box, what charge do I see? Nothing. So I look at that and say, well, I have no idea how that molecule reacts. I look at its resonance structure. Okay? And in particular, its first worst resonance structure. What do I see? Charge. So now when I think back to this compound that's drawn, I've got this resonance structure, not drawn out, but because I've been doing so many resonance structures and I'm sick and tired of them and I know how electrons move, that's what I see in my head. So that I now know that if I have a positive species, if I'm going to react this compound with a positive species, where's that positive going to be attracted to? The oxygen. If I throw in a negative species, where's that negative going to go? To the carbon, because that's where the positive charge is. So having an understanding of where the electrons are shifting within your structure predicts the chemistry. Okay? So that's one of the reasons why resonance is massively important. We'll keep coming back to it. And that's why in second semester, the answer to all questions why is resonance. Because in second semester, we hide all the charges so you can't find them. You have to look at the resonance to see where the charges are. Okay? Yes?
When we're drawing resonance structures, do we have to include the ones like that are more wrong? Or is it just the ones
So,
benzene?
when drawing resonance, and this is a problem depending on how different instructors like to look at things. I want to see the first worst. Okay? Because the first worst is really useful to me. I can get chemistry out of that. Okay? I don't want to see anything worse than it because I'm never going to see that chemistry. That's just not going to happen.
So you want to do
Okay.
all the ones that are
So-
neutral plus that one?
When we're asked to draw resonance structures, what you're being asked to draw are all of the structures of equal energy. So if asked to draw a resonance structure for this compound, you should be a bit baffled. Why? Your first resonance structure is charged, which means higher in energy. That's a bad structure. But if I ask you to draw the resonance structures for benzene, we started to draw some of those out, and our first few were all charged. But one of those last ones I drew was neutral. So if I ask for the resonance structures of benzene, I fully expect you, oh, that's a hexagon. I expect you to draw that structure. Okay? So when you're asked to draw resonance, focus on equal energy. There are cases where it's kind of questionable. And when it comes to the exam, I will try and throw at you only the cases where it's not questionable. When it comes to the homework, I'm trying my best to not hit you with those questionable cases. But usually when it's a questionable resonance structure, they are forcing you to draw those other resonance structures. How do they force you to do it? They give you another box. Okay? That other box means you should draw something else in that other box. Okay? So you, in the online homework, will get kind of forced into drawing those extra resonance structures. So does that make sense? Okay. Questions?
Well, on that other one, if that was the thing throughout the resonance structures, we would draw none?
You would draw none because there's nothing to draw. On an online homework, if they give you a box, you have to draw it. You don't have a choice. Never ask it on the exam. Okay?
So is that what we aimed for the one that we're trying to learn?
What was that?
Is that what we're going to get for that?
That's what you need to be seeing. So when we looked at that last structure, what I want you to do is to look for the first worst. You need to be able to see that. So when we talk about drawing resonance, it's a bit misleading because at least when we talk about it initially, you're only focusing for drawing good resonance. Okay? Remember how we said chemistry is about failure? That we learn a lot from wrong things? We learn a lot about the reactivity of this compound by looking at the wrong answer. Okay? So you have to be kind of familiar with the correct answers in this section because we unfortunately are begging for those correct answers. But after that, you want to be looking for your first worst. And there's still rules behind what make them worst. Remember, when we put the negative charge on the carbon, that was really bad because carbon is less electronegative than oxygen. It's not going to be willing to take those electrons away.
When you say first worst, are you saying like the better worst?
The first worst structure. So for this compound, we drew two resonance structures, okay, that were valid. Okay? We didn't exceed octets. We had one where a carbon was positive, and we had one where a carbon was negative. Okay? Of those two, if we ranked them, the best one is right in the middle, our carbonyl. Then it goes to our carbon being positive. Then it goes to our carbon being negative. The first worst one is because those first two aren't equivalent to each other. Okay? We'd have a ranking behind them. Kind of makes sense?
So it's the first least worst.
So it's the least
The one on the right is better than
Oh my gosh. The first least worst? Sure. Okay. I see how you're classifying it. I can agree with that. Okay. Formal charge versus oxidation state. Pretty much everything we're going to talk about this semester has to do with formal charge. Your textbook brings up oxidation state. We will look at redox reactions. At no point do you ever really need to know how to calculate the oxidation state in organic chemistry. So it's not that big of a deal. I would not stress too much on it. Okay, but we will go through and look at an example here on determining formal charge and oxidation numbers for both of these structures. So our formal charge, we've already got rule for. Okay, we got our equation in the second line. Okay, it's the balance of our shared electrons within a molecule. The oxidation number is the balance of electrons on an atom. What does that mean? Formal charge is about shared electrons, which means if I change the bonds, what happens to the formal charge? Changes. The oxidation number is the balance of electrons on an atom. If I change the bonds, do I care? That doesn't change the atom. It's still the same atom. So our oxidation number will not change when we rearrange bonds. Okay? But our formal charge, wow, there's definitely something in my eye. The formal charge will change. So if we go through and take a look at both of these structures, I'll just be a pirate for the rest of the day. We'll get negatives on all of these oxygens. Okay. We'll get what charge on the sulfur?
+2.
How'd you come up with a +2 so fast?
Sulfur has, what is it? -2.5.
One option is going through the big long calculation, or we know that we're looking at sulfate ion. And sulfate ion has what charge? -2. If we've got 4 minuses on the outside, what does the sulfur have to be? +2 to cancel that out. Right? If we look at our formal charge on the other one, our oxygen will be minus, oxygen will be minus, and our sulfur S will be neutral. Okay? So this is where it comes from looking at Lewis structures. According to organic chemistry, and depending on how you were taught in Gen Chem, the correct structure is the one on the right, because the one on the right has less charge than the one on the left. Okay? That's our big change in moving up into organic chemistry. And based on the quizzes, we're split roughly 50-50 on people being trained to use just the single bonds versus actually bringing in the double bonds in this case, okay, to expand that octet. So we've got to be careful when we deal with our structures and how we apply these things. So our formal charge was red. And please forgive me, you may have to walk me through the oxidation numbers. Okay, I wrote down the formulas because I needed to be careful with this. Balance of electrons on an atom. So it's the valence electrons minus the electrons owned by that atom. Okay, so I'm just going to do sulfur. How many valence electrons does sulfur have?
6.
6. So now what we'll go through and do is look at the electrons owned by the sulfur in this structure. So what do we mean by owned?
The ones that it started with.
We look at this bond and say, does sulfur own any of those electrons? Ah, we heard a yes and no. That's fun. For the no's, unfortunately the no's have it. What's the no's? That says it doesn't own any electrons. If it's sharing, that says it does have electrons. Oxygen is more electronegative than sulfur, which means what does oxygen do with all of those electrons? Takes them. So sulfur has no electrons owned in that bond. How about the other bond? Another bond. Other bond. It owns no electrons. So we end up with a +6. What happens when we move over to the other sulfur? How many valence electrons does sulfur have?
6.
6. Minus, how many electrons does it own? Still none, because it's still bound to the same atoms. Okay? Yeah, there's multiple bonds, but I don't care about the multiple bonds. I'm only looking at the atoms attached to it. Oxygen is still more electronegative. Sulfur, again, owns none of those electrons. The oxidation state comes out at +6. All right? So our oxidation states will stay the same regardless of what resonance structure we're looking at. Okay? But the charges may change. Okay? So the oxidation states don't help us out as much. Because if we look at sulfate and we want to think about its reactivity, we look at the oxygens as being negative. Okay? And all of those oxygens are equally negative. If we look at, if we look at the one Lewis structure that we drew here, that makes it look like only the oxygens on the left and the right are negative and not the top and the bottom. Right? So we lose some information depending on how we go through and look at our individual questions. Right? Formal charge is going to be the most relevant, the most useful for us to go through and use. That's the one we're going to be sticking with. Questions? So best Lewis versus useful. Our useful, let's see if I can get this right, is our first least worst Lewis structure. Okay? So it's not the absolute worst one, but not the best one. Okay? That's going to be our useful Lewis structure. The best Lewis structure has to follow these certain rules for it being best. The primary rule is satisfying the octet, which is why when we go back to our Lewis structures for sulfate, okay, the one on the left is not our best Lewis structure. The one on the right is. Because the formal, or sorry, that's not octet. When we look at our carbonyl compound. Oops, I now remembered it. I've got the example right here. Give me a sec. CH3CO+. We've got CH3, C, plus. And let's get in our lone pairs. This structure is technically our useful structure, not our best Lewis structure. Okay? And it's all because of rule number 1, satisfy the octet. What atom does not satisfy the octet in this structure? This carbon has not satisfied its octet. Our oxygen has 2 lone pairs and then 2 bonds, so it's got its 8 electrons. That carbon has not satisfied its octet. So that structure is actually only the useful one, not the best one. What do we have to do? Move a pair of electrons down, and what we end up with for our best Lewis structure is this one. We're going to get into Vesper stuff, so let me be a little more careful with that. We end up with this structure. And I think I heard a little woo there. If we compare these two structures, based on what we've been talking about, which one do you think is best? Gut instinct, you look at it and go, that's the one I like. You probably go, the right one's better. Why? Does oxygen want to be positive? No, because it's the most electronegative. Where it went positive before, it was also under its octet. Does it have its octet here? Yeah. Okay. This structure, our red one, is actually our best Lewis structure. The purple one is our most useful. Okay. So we have to be careful on deciding best versus useful when we go through and work with our individual reactions. When it comes to Lewis, we're looking for satisfying that octet. Number 2, minimize charge. That's our issue with our sulfate structures. Okay? The one on the right minimizes the charge on the sulfur. It's neutral in the right structure. The one on the left has a +2. Okay? There are other examples that float out there. I don't remember what those are. They're usually pretty rare. It's those first 2 that you see happen all the time. One of the reasons why I don't spend that much time looking at it is because I primarily focus where? Useful. I don't care about a rule that says that this thing is red and this is blue. What does the red thing do? What does the blue thing do? Okay, so when we're looking at structures and when it comes to nomenclature, it's the same thing. I hate nomenclature. Why? Because we determine nomenclature based solely on, I still got 2 minutes, solely on an arbitrary rule, and that is it. Right? So I hate nomenclature. There's no understanding behind it. If you know the rule, you can name it. If you don't know the rule, you fail, and it sucks, because there's no other way around it. Right? So almost everything that we talk about in this class is going to be looking towards useful. That said, Lewis structures. Right? The idea is that you do tons and tons and tons of these until you build up common patterns. Remember, our periodic table is condensed. We don't have to worry about the entire thing. Right? What we've got on here is only a list of, I can't, count. 5 things, but our halogens count up for 4. Right? So we've got 9 different elements on here. You should be going through and doing a bunch of Lewis problems or Lewis structures with each of these compounds, and eventually you build up this habit or this instinct that if you see boron, if it's neutral, it has 3 bonds. If you see carbon and it's neutral, it has 4 bonds. Okay? So you pick up these habits and you recognize what's happening with it. When we move into nitrogen, oxygen, halogen, you recognize the bond patterns and, more importantly, you recognize the lone pairs. What happens if we go through in charged states? Our charged states also pop up. If we've got a carbon with only 3 bonds, then it by definition has to be positively charged. Okay, so you build up these patterns. You either do that by doing lots of practice, or you memorize this nice little table that shows it all for you, so that when you look at a structure, you can very quickly say, that carbon has 5 bonds, wrong. That nitrogen has 3 lone pairs and 2 bonds, wrong. Right? Because those aren't possible states. I'm going to jump straight to here. Whoops. our organic simplifications, just to end on. Feel free to pack up. I'll just kind of talk through some of these. We're concerned with our 8 elements. We get simplified shapes and hybridizations. We haven't quite talked about those yet. But in our drawings, this is where it becomes really important. Every point is a carbon unless you otherwise tell it. Hydrogens are often, though not always, implied to carbon to satisfy an octet. Right? This is why when I drew out benzene, I could just draw all the dots and not draw on any hydrogens, because hydrogens are often implied. Charges are never, ever, ever, ever implied. Okay? If an atom is charged, you must specify that it is charged. Okay? The main reason being hydrogens are implied. If we imply charges, then we can't imply hydrogens. It doesn't quite work. Okay? Nitrogen, oxygen, and halogens will often have their lone pairs implied. Okay? 2 dangerous cases. Our lone pairs are implied, and our hydrogens are implied to carbon. What if you have a hydrogen bound to oxygen? It's not carbon. Don't imply it. You have to show it. Okay? Thank you for your patience. We're done.